Okay, so welcome friends. Welcome to NEET Rapid Revision Series. Today we are going to discuss the lecture number 11 that we have. Two chapters we have, that is electromagnetic induction and second is alternating current. So this chapter, together this chapter, so one unit we describe and that will be having this. These are the topics that we are going to discuss. What is Faraday's laws of electromagnetic inductions? Next we have Lenz's law, motional EMF, self and mutual induction. And AC circuits, we have different types of circuits here. There will be only inductance will be there will be only capacitance will be there will be only resistance. Then we have combination of the impedance and resistance. Then we have combination of the resistance and capacitance. Then we have combination of the resistance, capacitance as well as inductance. So this circuits we have that is coming the alternating current over here. I hope you all are doing very well practice. This some electromagnetism. This is the last chapter for the electromagnetism. Tomorrow we'll be coming with optics. So let's discuss what are the weightage wise. If we see, we can expect one question from each chapter, one or two questions from each chapter, that is alternating current as well as electromagnetic induction from this unit. Okay, so let's begin our journey of today's class. So magnetic flux, what do you mean by magnetic flux? Okay, so right. So what is a magnetic flux? It is the magnetic flux is a physical quantity which is proportional to number of magnetic lines passing a given area perpendicular to it. So if we have this particular case, do we have this? Let's say this is the area over here, and these are the magnetic lines which is directly passing through this. So like this, if we talk about this, these are the magnetic lines which is directly passing through given area. Area vector, we always take that perpendicular to given area. This is the area vector we have. This will be area vector over here. This particular angle will be theta, and these are the magnetic field lines. So magnetic flux is defined as dot product of area vector and magnetic field. So that is B dot A. So here we can write here phi, and what is phi? The phi value will be given by phi is equals to B A cos theta. What is theta? Theta will be the angle between the magnetic field and area vector. Keep this in mind. So we have different cases over here. This particular case where the magnetic field lines is directly crossing the given area. In this case, area vector in the same direction, magnetic field also in the same direction. Theta equals to 0. When the theta is 0, cos theta is maximum. So here we'll be writing this phi is equals to B A cos 0. So phi is equals to B multiplied by A. What about this one? If we have the area surface like this and magnetic field lines are passing like this. So this is the area vector and magnetic field lines are passing like this particular way. These are the magnetic field lines that is passing through this, and this is the area vector we have. So in that case, what will happen? So this is the magnetic field line that is passing and this is the area vector. So when the area vector and magnetic field line are perpendicular to each other, then this is what we define. This will be defined as zero flux because angle is 90 degree here. And other cases we have flux is supposed to be a cos theta. If number of turns is also there in a given coil, 1 turn, 2 turn, 3 turn, 4 turn, like that, how many turns? N turns will be there. So magnetic flux in that case will be writing just multiplied by N. Phi is equals to N B A cos theta, where N is the number of turns through the given coil. 1 turn, 2 turn, 3 turn, like that we have different turns. Number of turns will be there, that is NBA cos theta. So this is the magnetic flux we have. Next we have, that is this Faraday's laws of electromagnetic induction. So how the Faraday's law of electromagnetic induction? What is the property of this? What is the Faraday's law of electromagnetic induction? So Faraday's, we have seen the AC generator. We are using the electricity that is coming from the power plant. In the power plant, what is still happening? So we have seen that thermal power plant. We also know the different kinds of power plant. In all kinds of power plant, there is one phenomena that is common. That phenomena is, we define, electromagnetic induction. So electromagnetic induction, it is the phenomena in which electricity is produced by changing the magnetic flux. So whenever there is magnetic flux changes with the coil, EMF is induced across the coil. This phenomena is what we define electromagnetic induction. This phenomena is what we define electromagnetic induction. And this is also given by Faraday's laws of electromagnetic induction. The first law, that is EMF, that is whenever magnetic flux linked with the coil changes, then EMF is induced. If coil is closed, then current will also be induced. Faraday's second law, Faraday's second law says that whatever the EMF that is induced, that is given by E is equals to d phi by dt. The magnitude of the induced EMF is given by E is equals to d phi by dt, that is rate of change in magnetic flux. So mod of A is equals to this, that is d phi by dt, rate of change in magnetic flux. This is given by Faraday's second law. The magnitude of the induced EMF is d phi by dt. This one is instantaneous value of the EMF. If you talk about the average value of the EMF, the average value of the EMF is given by delta phi by delta t. And what is delta phi? Change in flux. And what is delta t? Change in time. So change in flux with respect to time will give us induced EMF expression. Now, how can we change this? So just now we saw that whenever flux changes, for example, if the coil is approaching the magnet or the magnet is approaching the coil, the number of field lines which is directly falling on this particular coil will change if the coil is approaching the magnet or if the magnet is approaching the coil. Whenever there is relative motion between the magnet and the coil, the number of field lines which is passing through this particular coil will change. As the field line is changing, what will happen? If the field line changes, what actually happens that more number of field lines will come. With time, the magnetic field lines on the coil changes. Whenever the magnetic field lines on the coil changes, there is induced EMF across the coil. If the coil is closed, then current will also be induced. So here that we are going to discuss, that is ways to change the magnetic flux. So what is magnetic flux? Phi is equals to N B A cos theta. So how can we change this flux? Flux can we change by changing the magnetic field? Yes, flux can be changed by changing the magnetic field. And E we can write here in this particular case, E is equals to d phi by dt. If only B is changing, other term is constant. This is N A cos theta into dB by dt. What is N here? Number of turns. A is the area of the coil. Theta is the angle between the area vector and magnetic field. By changing the area, effective area, this will be discussing by changing the effective area. So if area is also changing, so what is EMF we can write here? E is equals to this, area is also changing and magnetic field is also changing. So NB cos theta into dA by dt. If area also changes, this will can write here NB cos theta into dA by dt. If area changes. Second is by changing the angle between the magnetic field. This is what happens in case of the power plant, that is electromagnetic induction, that is rotation of the coil in the magnetic field. So if the magnetic field rotates, because of the rotation of the magnetic field, what actually happens that the coil is rotating like this particular way. So that orientation of the coil changes with time. So if this coil rotates, because of this rotation, this theta changes. When the theta is changing, magnetic flux will change. So here we can write E. What is E? D phi by dt. And when this coil is rotating, we will be writing this NBA omega cos omega t. Right? If you differentiate this particular term, we will be getting this NBA omega sin omega t. So that is what we are getting this EMF. NBA omega sin omega t. So this is what induced EMF. Last one is that changing number of turns. Does this happen? Changing number of turns. If you change the number of turns, does it actually happens? So if we change the number of turns, this is not physically possible that we are changing number of turns each and every time. No, this is not physically possible. So this is not we are considering over the different questions over here. So let's discuss how we can change the fluxes over here. So first one we discuss, that is by changing the magnetic field. If the magnetic field value is changing, flux will change. By changing the effective area, either coil area will keep on increase or area is coming out, means coil is coming out of the magnetic field, coil is going into the magnetic field. In that case also this area will change. Second, angle between the magnetic field. So if this coil is rotated in magnetic field, theta changes. And how theta changes? Theta is omega into t. So for that, this is also principle of AC generator. And what is EMF in this particular case? E is equals to N B A omega sin omega. So this is what EMF we are getting, N B omega sin omega t. Right. So next we have Lenz's law. What is Lenz's law? Lenz's law gives the direction of induced current in a such a way that it always opposes the change. It will always oppose the cause which have produced it. So the Lenz's law of induced EMF in a coil is such that it always opposes the cause which have produced it. Mostly oppose the causes. So most of the students get difficulty here in the direction of this. It is very simple. It will oppose the cause which have produced it. If the cause is increase in magnetic field, it will try to decrease it. If the cause is decrease in magnetic field, it will try to increase it, and vice versa. So let's see some of the cases in which the Lenz's law will be clear, very much clear. Give the direction of induced current in each of the case below. First case is what? Magnetic field going into the plane increasing or decreasing. So magnetic field it is going into the plane. Okay, first let's say magnetic field is increasing and there is one coil that is at this particular point. Let's say there is one coil. What we want, the magnetic field which is going into the plane, let's say it is increasing. So we want to decrease the magnetic field, we have to give the direction of the current in such a way that that should tend to decrease the magnetic field. So magnetic field which is going into the plane is increasing here, we have to decrease it. So we have to give the direction of current in such a way that that should oppose it. How can we oppose it? By giving the magnetic field outside. So in this case, magnetic field should be outside. It's only possible when the current is anti-clockwise. Rotate your fingers in the anti-clockwise direction. Because of this anti-clockwise direction of the current, your thumb is outward. Thumb outward gives the direction of the magnetic field because of this induced current, and that is outward. So magnetic field inward is increasing, but we are giving magnetic field outside by giving anti-clockwise current. So in this particular case, current will be anti-clockwise in this manner. Suppose in the second part, where the magnetic field decreases with time, and we have the coil placed in decreasing magnetic field. So what will the direction of induced current in that case? So let's check. So because of this, now magnetic field which is going into the plane is decreasing. Okay, which is going into the plane is decreasing its value. We want to increase the magnetic field. How can we increase the magnetic field? We have to give current in a such way that it should give the magnetic field in the same direction, and because of that current carrying coil, magnetic field will be along this direction. So I want to give magnetic field towards inside, so I have to give the current value in this particular direction. So if I am giving this particular direction, rotating my fingers in this direction, thumb is going which side? Inward side. So in this case, the current here will be clockwise if the magnetic field is decreasing. So this is how we are getting the Lenz's law. Let's say some more scenario. A coil is placed near the current carrying coil and current is increasing and decreasing. So let's say I am placing one coil and this particular value, and this current is increasing. So just now we saw that because of this increasing current, so what actually happens? Because of this increase in current, so what will happen? I value increase. If the I value increases, so what is the magnetic field here? That will also increase. Okay, that will also increase, and that will increase because I is increasing. What is magnetic field? B is proportional to I. So I is increases, magnetic field will also increase. Magnetic field which is going into the plane increases. So what is the direction of the current? Should oppose this. And how it can oppose this? It will oppose in this particular direction. So this will be direction of current. In this case, it will be anti-clockwise. It will be anti-clockwise. Suppose if reverse case, that is we are having the current direction like this way, and at this particular point, suppose I want what is the direction of the induced current. So here now let's say current is decreasing with time. So this main current decreasing with time, because of this magnetic field is again inward only, but this magnetic field also decreases because magnetic field is proportional to current. So what will happen in this case? Magnetic field is decreasing going inward this side. So here we'll be writing current will be in this particular direction. So that magnetic field has to increase if it is going inward. I hope this is clear to everyone. So this is how we are getting the Lenz's law. Magnet brought near or move away from the coil. Suppose if this is the coil over here and magnet is there, north pole and south pole. So whenever, one thing that we should keep in mind is that if north pole is approaching the coil, then there will be a repulsion. If the magnet wants to come to the coil will repel it. If the magnet wants to go away from the coil will attract it. So this north pole is approaching, so here will be repulsion force will only happen if this side also in north pole is there, and this side will be getting south pole. Because as the magnet is approaching the coil, so there will be repulsion. So it's like brother and sisters. Okay, brothers and sisters coming closer, they will fight with each other. When they are moving up from there, they will love each other. So like the same thing is happening here also. So north pole is approaching, so here also north pole is there, so that they will repel each other, and this side south pole. When this side north pole is there, if we see from this side, north pole means, yes, we discussed yesterday that which kind of current, it will be anti-clockwise current. If I see from this side, it will be clockwise current like this. If I see from this side, it will be clockwise current like this. If I see from this side, it will be anti-clockwise current like this, right? On the other hand, suppose if the coil is there and suppose south pole and north pole. Now south pole is moving away from here. In this scenario, let's say magnet is moving away from here. Now the magnet is moving away from here. This particular person will try to attract it. And how we can attract it? By giving the current north pole, by giving the north pole direction, and here south pole. Again, if you see from this particular side, it will be anti-clockwise. Like this, it will be anti-clockwise. If I see from this side, it will be clockwise, because this side it is south. So this is how we'll approach the given problems from the Lenz's law. Magnet falls through the coil. Simple is there. So this side, if the north pole is falling, if the north pole is facing to the coils and the magnet is falling, so here will be getting north pole and here will be getting south pole. Repulsion will be there because of this A is less than G. On the other side, suppose even if it has crosses the coil and this is falling down, so this is falling down means moving away from the coil. So this side north pole and this side south pole. Now there will be attraction upward side. So again A will be less than G, right? Current increases or decreases in the concentric loop. So there is one loop over here and there is another loop over here. Current value increases or decreases. So let's say I value is there and this one is let's say main current. Okay, this one is main current. If I value increases, what will happen? Because of magnetic field. So let's say this is the outer current carrying coil carries current in this direction. Because of this magnetic field at the location of this will be given by outside. Okay, will be given by outside. Now what I am saying, I increases. Suppose if I increases, so I increases. So this B value will also increase because this I is giving B. So this B also increases. Now outward magnetic field is increasing. Outward magnetic field is increasing. We want to decrease that outward magnetic field. How can I decrease outward magnetic field? By giving the magnetic field inward. I want magnetic field should be inward. So direction of current should be, in this case, here the direction of induced current should be in a such way that because of this direction, the magnetic field should be inward. So here, if this one is I and this one is induced current, both will be in opposite direction if current increases. And this is also principle of self-induction also. So here I and this is induced current, both will be opposite direction if main current is increases. Remember this line. Second, if we have the coil is there and if we have, let's say, in this particular manner, suppose current is, this is main current and this value is decreasing. So because of decrease in magnetic field, the magnetic field which is going into the plane also decreases. I have to increase this magnetic field. So for that again, the direction of current has to be clockwise so that magnetic field should go inside. So here this induced current and this main current will be in the same direction if current is decreased. This point should be clear to you, right? This point you should keep in mind. So let's say here in this particular case whether the current is increasing or decreasing. So here if the coil is entering the magnetic field over here, as the coil is entering the magnetic field, this particular coil is entering the magnetic field, its area will increase or decrease? Area increases. Okay, area increases. Area which is falling under the magnetic field increases. We have to decrease that. And how we can decrease that? By giving the magnetic field outward direction. And how can we give the magnetic field outward direction? By giving anti-clockwise current. Okay, next, this coil is coming out from this, so here the flux decreases because area decreases. Okay, area decreases, because of that flux will also decrease. So as the flux will decrease, area will decrease. So flux will decrease, area decreases, flux decreases. We have to increase that. And how we can increase that? By giving the current clockwise manner. So in this, current will be clockwise. Here current will be anti-clockwise. Okay, here again it is coming out. As it is coming out, I told you if it is coming out, area will decreases, area decreases. The magnetic field constant, but magnetic flux decreases. The magnetic flux decreases, we have to increase it. So we have to increase the magnetic field which is going into the plane. So here the current should be clockwise again. I hope this is clear to everyone. And if the coil is inside, it is moving, no EMF will be induced because this coil is having constant area and that is inside the magnetic field, it is moving. If it is coming out, EMF will be there. If it is not, EMF will not be there. Okay, so these are the points that we should keep in mind. So let's solve some of the basic questions from this. Starting from magnetic flux, the net magnetic flux through any closed surface is 0. Integration of B dot ds is equals to 0. This is for any closed surface. The Gauss law of magnetism will discuss it. So this will be, answer will be option D. A square loop of side 1 meter resistance 1 ohm is placed in magnetic field of 0.5 Tesla. If the plane of the loop is perpendicular to direction of magnetic field. So let's say magnetic field is this particular direction which is going into the plane of this board. going inside plane of the board, the magnetic flux through the loop should be given by, so they have given the square loop, and the square loop, they have given the resistance, they have given the side length, and magnetic field value is also given. What is it asking? The direction of magnetic, what is the magnetic flux of the loop? What is magnetic flux? So even whatever the current is flowing over here, we can calculate the flux. Flux depends on two things, that is B A cos theta and B A cos theta. And what is n value? 1, only 1 is a square loop they have mentioned over here. 1 into magnetic field, 0.5 into area of the coil we know, 1 square into cos theta. What is theta? Area vector and magnetic field ki beech ka angle. So this area vector is going inside and magnetic field is also going inside. So if this is the area, magnetic field in area both are in the same direction. So this will be cos 0. So this is what we are writing here, 0.5 Weber. Weber is the SI unit of magnetic flux. Okay, 0.5 Weber. Right. Next we have, the question is coming from this, that is magnetic flux linked to the circular coil of radius r is given by, so phi is equal to 2t cube plus 4t square plus 2t plus pi. So they have given the magnetic flux, and what they are asking, the magnitude of the induced EMF. What is induced EMF magnitude? We have this d phi by dt. So just differentiate the given term over here. Differentiating the given term will be getting this. This is 3t square plus 8t plus 2. At which particular time they are asking? T is equal to 5 seconds they are asking. T is equal to 5 seconds they are asking. So from here we will be writing what is EMF? 3 into 5 square plus 8 into 5 plus 2. That will be getting here. So this what we are getting? So 25 into 3, this 75 plus 40 plus 2. Sorry, this is 2t. So this will be 6. This will be not 3t square, this will be 6. Okay, this will be 6. So this is 150 plus 40 plus 2. What we got here? 192 volt. Answer is option A. So simple question, that is E is equal to d phi by dt. Okay, right. Next we have a coil of resistance 400 meter. So you can note down the expression for the induced EMF and charge. Expression for current, expression for I and charge. So expression for I and charge. So just now we got what is E? EMF. What is EMF? Delta phi by delta t or d phi by dt. EMF we can write from the Ohm's law, I multiplied by R is equal to delta phi by delta t. So what is I? I is 1 by R delta phi by delta t. And suppose if I write I, what is I? Delta q by delta t, and that is given by 1 by R delta phi by delta t. Delta t cancel. What is delta q we are getting here? Delta phi divided by R. So this particular expression we are getting. In this particular expression we can check that charge depends on change in flux and resistance, and here current depends on resistance as well as change in flux and time. So I is equals to 1 by R into d phi by dt. This is d phi by dt is the magnitude of the induced EMF. That's it. 1 by R. What is R? 400 into d phi by dt. What is d phi by dt? 100 t plus 0. At which time they are asking? 2 seconds. Putting the value 2 seconds over here. So 1 by 400 into 100 into 2. We are getting how much? 1 by 2 ampere. Answer is 0.5 ampere. And this is the expression for the charge. Delta q equals delta phi by R. Delta phi is the change in flux divided by resistance. A long solenoid of diameter 0.1 meter has a 2 into 10 to the power 4 tons. So number of tons of the solenoid they mention is 2 into 10 to the power 4. Okay. Next we have at the center of the solenoid a coil of 100 tons and radius 0.01 meter is placed. 0.01 meter is placed. So it's placed with axis coinciding with the solenoid axis. The current in the solenoid reduces at the rate of 0 ampere from 4 ampere in 0.05 seconds. If the resistance of the coil is 10 pi square ohm, the total charge flowing through the coil during this time is given by. So total charge. So magnetic field value is given how much? The magnetic field value Okay, they have not mentioned the magnetic field value. We'll be calculating because of the solenoid. What is that? Mu naught into N into I. Okay, a number of turns they have mentioned, and diameter also they have mentioned. The solenoid has diameter 0.1 meter, has this many number of turns per meter. At the center of the solenoid, a coil of 100 turns and radius 0.0 meter is placed with its axis coinciding with the solenoid axis. The current in the solenoid reduces the constant rate of 0 to 4 ampere in 0.05 seconds. Okay, with the resistance of the coil. So what they are asking, charge. What is a charge? Delta Q. What is delta Q? Delta Q is given by delta phi by R. So delta Q is equal to delta phi. What is delta phi? Change in flux. NBA. So what is, you can change, you can check what is changing here. 0 to 4 ampere. Current is changing. So because of change in current, there will be change in magnetic field also. So here we can write here. So B1 to B2, number of turns is same. Area will also we can calculate. So this side N B1 A cos 0 minus N B2 A cos 0. Okay. So this side divided by, that's it, divided by resistance. What is resistance? R. So this particular term delta Q we can write here N common. So this will be given by B1 A cos 0 minus B2 A cos 0. So B1 A cos 0. Area is also outside N A. This side B1 minus B2. Right. So divided by this resistance R. So putting the values over here. This is NA mu naught into N divided by I1 minus I2 divided by resistance R. That's it. Putting the values, so delta Q, what is delta Q will be getting here? Number of turns they mention is 2 into 10 to the power 4. Right. Multiply by this area. What is area? Whose area? We have the area of the coil. What is area of the coil? A center of solenoid, a coil of 100 turns and radius is 0.01 is placed with the axis coinciding with the solenoid axis. So number of turns is, sorry, this one is 100 multiplied by area. So what is area? Will be writing this pi into 0.01 square into. So this is area we are getting, multiplied by this mu naught 4 pi into 10 to the power minus 7 into N is the number of turns of the solenoid, that is 2 into 10 to the power 4. 2 into 10 to the power 4 into I1 minus I2, that is 4 minus 0. Divided by resistance. What is resistance value? They have mentioned. The resistance value is 10 pi square. So this will be 10 pi square. This pi square get cancelled. So remaining thing that we can solve it. So this one is 2 into 4. 2 into 4, 8. 8 into 4, 32. So here we are getting 32 microcoulomb because pi is cancelled everywhere. Okay. A conducting circular loop is placed in uniform magnetic field. B is equal to 0.025 Tesla. So B is equal to 0.025 Tesla. When it is plane perpendicular to the loop, the radius of the loop of is made to shrink at constant rate of this much. The induced EMF. If the radius is shrinking, the area will also change. The area will also change if the radius is shrinking. So in this case, we'll be writing this. What is area? The area is given by pi r square. And what is the number of turns? A conducting circular loop means number of turns we can take it as 1. And they're asking induced EMF. What is induced EMF? E is equal to d phi by dt. So from here we can write here that is d by dt of phi. What is phi? NBA cos 0, because the coil is, magnetic field is like this and the coil is placed in this particular manner, like this the coil will be placed. Okay. So here area vector and magnetic field angle will be 0 degree. So from here number of turns is 1. B, take it outside. B into d by dt of pi r square, and from here we can write here B into 2 pi r into dr by dt. So B, what is B value? 0.025 Tesla. 0.025 Tesla multiplied by pi multiplied by r. What is r value? Radius is how much? 2 centimeter. 2 into 10 to the power minus 2 multiplied by dr by dt. How it is shrinking at the rate of how much? 1 mm per second, that is 10 to the power minus 3. So this we are getting 0.025 into 2. How much will be getting? 0.025 into 2. This is 0.05. Okay, 0.05. That is we are getting 0.025 multiplied by 2, and one more 2 is there. This 2 pi r is there, na, pi into r. So multiply by this 2 also. So So we are getting this 0.025 into 2 into pi into r. So this 2 into 2, 4, 4 into 0.025, 0.1. So we are getting approximately this pi microvolt. Okay, this will be pi microvolt. Okay, right. Moving next question, that is coming from the AC generator. I told you the formula for the AC generator. What is that? If the coil rotates in a such a way that it is rotating like this particular manner, the coil rotates. So this one is the coil. If it is rotated about this particular point, about this particular axis, if the coil is rotated like this, okay. So what is the induced EMF magnitude we have just now? That is NBA omega sine omega t. What is omega here? Omega is the angular velocity with which it is rotating. An EMF generator by a AC generator having how many turns? 100 turns. Loop area 1 meter square. So this area that we should know, that is 1 meter square, and it is rotated like this. When it is rotated like this particular manner, in this particular manner, what is induced EMF? We have NB omega sine omega t. So let's see, and what is maximum value from here? This is the maximum value that we'll be getting. So E max is equals to NBA omega. So what is E max? Number of turns. What is number of turns? 100 into magnetic field 0.05 into area vector. What is area they have mentioned? Area they have mentioned how much? 1 meter square. Right. Next. At a speed of 1 revolution per second. At a speed of 1 revolution per second. 1 revolution per second. How much is speed? 1 revolution per second. If we convert into radian, 1 revolution means 2 pi radian per second. So this is what we have omega. Okay, 2 pi radian per second into 2 pi radian per second. This is what we have omega. Now solving this particular case, we will be getting this 0.05. This is pi into 2. We are getting this 10 pi radian per second. So 10 pi radian not required. So this 10 pi volt will be here. So answer is 31.4. Pi is 3.14. So motional EMF, we talk about this. If any conductor is moving, in perpendicular magnetic field, then motional EMF is given by, if conductor is moving like this way, if any conductor is moving in perpendicular magnetic field in this way, then motional EMF is given by E is equals to BVL. What is B? Magnetic field, which is going into the plane, and what is V here? Velocity, and what is L here? Length. When to use this particular formula? Provided that magnetic field, velocity and length should be mutually perpendicular to each other. In that case, we'll be using this particular formula BVL, right? And suppose if you have a curved wire like this, and what is direction of this? We have to use our right hand palm rule in such a way that this orientation of the hand should be going, that is orientation of these fingers. The direction of the fingers should be going in the direction of the magnetic field, and this thumb should represent the direction of the velocity, and this where the palm is going, that side will be high potential. So this will be high potential, and opposite side of this will be low potential. This will be high potential and this will be low potential. This thing that we should keep in mind. So this high and this will be low potential. In case of the curved wire, what we have to do? Just join by end points. This will be L effective. Okay, this will be L effective. And what is magnetic field? What is EMF induced across this? B into V into L effective. And what is L effective here? B into V. So this one is R, this will also be R. So this will be 2R. In case of the curved wire, we'll be joining their endpoints, and again, as it is falling down, in this case, as it is falling down, we have to place our hand in such a way that magnetic field is going towards this side, and as it is falling down, this will be high potential, and opposite side of this will be low potential. So this R will be high potential, and this will be low potential over here. So this one is low potential. This is falling down. So what is the magnetic field? BV into 2R, that is 2R into BV, and R is at higher potential. Okay, R will be at higher potential. In which of the following devices the eddy current is not used? What is eddy current? So in general, whenever a metal is placed in varying magnetic field, whenever any metal is placed in varying magnetic field, a current is induced. Any metal is placed in varying magnetic field. So if current value, if current is there, any metal is there, metallic surface is there, if this is placed in varying magnetic field, so there will be induced electric field that is generated. Because of that, current is generated like this in a circular manner. So this current generated because of the change in magnetic field across the surface of the conductor. Okay, this is what we define eddy current, and this eddy current is also called it a circular current or whirlpool current that is generated because of the change in electric flux. We are using this, is not used, we use in induction furnace, we use in electromagnet also, we use in electromagnetic braking train. We don't use electric heat in electric heater because this one is, we can say, this is purely resistive circuit, right? So here heat is directly passing through the resistor in that case. In a coil of resistance 10 ohm, the induced current developed by the changing magnetic flux through it is shown in this figure as a function of time. The magnitude of the change in flux through the coil in Weber will be given by through the flux in the change in coil in Weber. So right now, this graph is I versus T. Remember this, whatever the area of this graph, that is I multiplied by T, will give us charge. So area will give us charge, right? How much charge that has flown through the coil in how much second? 0 to 0.1 second. So we'll be getting this area will give us total charge. And what is total charge? We can calculate from here area. What is area? Half into base. What is base? 0.1 into height is 4. So we are getting this, how much? 2 into 4, that 0.2. This is the what we are getting the charge. Okay. And what we have, the expression for induced charge and EMF will be given by this. Delta Q is equal to delta phi divided by R. What they're asking? The magnitude of the change in flux they're asking. So what is delta phi? The delta phi is equal to R into delta Q. What is resistance? 10 multiplied by delta Q. What is delta Q? 0.2. So this one is 2. This will be 2 Weber. Self-induction. So we have the formula for the self-induction. So a current of 2.5 ampere flows through the coil of inductance 5 Henry. The magnetic flux linked with the coil. So phi is proportional to I. Okay. So phi is proportional to I. And what is the constant? We have L. And that constant is given by L. What is L? Phi by I. So flux, we know how much. Current, we know how much. 5 Henry. Current, we know 2.5. They are asking the flux, we will be using this particular formula. So phi is equal to L into I. What is L? Phi multiplied by 2.5. Answer will be 7.5. We are getting this. Sorry, 12.25. 12.5 Weber. So this induction, that is phi is proportional to I. Second is induced EMF. They are asking L into d phi by dt. So L, this is E is equal to d phi by dt. And what is phi? The phi we have L into I. So from here we can write E is equal to minus d phi by dt. When we have E is equal to minus d phi by dt, minus d phi by dt. So from here we can write here E is equal to minus d by dt of phi. What is phi? L into I. So this L is constant minus L into di by dt. This is induced EMF. If you talk about the average value is given by minus L into delta I by delta t. Instantaneous, this one is instantaneous value only, that E is equal to minus L into di by dt. What is di by dt? Rate of change in current. Okay, rate of change in current. Rate of change in current. A long solenoid has 1000 turns. When a current of 4 ampere flows through it, the magnetic flux linked with each turn of the solenoid is 4 into 10 to the power minus 3 Weber. The self-induction of the solenoid is given by. So again, the phi is equal to L into I. So what is the, when a current of 4 ampere flows through it, the magnetic flux linked with each turn of the coil. So what is total flux? Phi is equal to L into I. What is total flux? The total flux that we will be getting is N into phi of each turn. So how many turns will be there? Different turns will be there. The flux through each turn is phi. So like that, how many turns? N turns are there. So this will be total flux will be phi total is N of each turn. So this will be writing here N phi of each turn is equal to L into I, where L is the inductance of the solenoid, I is the current. That's it. So what is the number of turns? 1000. And flux to resistance is how much? 4 into 10 to the power minus 3 equals to L into what is current that is flowing through it is 4 ampere. 4 or 4 cancel. This also getting cancelled. What is L? L is 1 Henry. So answer is 1 Henry, that is phi is equals to Li. So this is how we are solving. Otherwise, direct formula for this inductance of the solenoid is, self-inductance of the solenoid is L equals to mu naught N square pi r square small l. Okay. What is R? R will be radius of the solenoid. Second is, we can write here mu naught N square pi r square divided by capital L. By small l again. This is capital N. Small n is number of turns per unit length. Okay. So in terms of the number of turns, this is in terms of the number of turns per unit length. Right. Two conducting. So next is mutual inductance. Mutual inductance happens whenever the current changes in one coil, EMF induced in other coil. That phenomena is we define the mutual inductance, mutual induction, and we have that one particular term that is mutual inductance, which governs the property of mutual induction. So here in this case, if we talk about this, for this particular case, two conducting circular coil of radius R1 and R2. So this one is in a such a way that their centers are coinciding. R1 is very, very larger than R2. What they are asking, mutual inductance M between them is directly proportional to. So mutual inductance is given by M is equals to mu naught N1 N2 pi R2 by 2R. Okay, pi R2 by 2R, 2R1. Now, this is the direct formula for mutual induction of the two coils. Concentric coils should be there, and this particular term, that is pi R2, should be inside. This is a smaller one, and this one is larger one. And this number of turns, for this coil we can say number of turns is N1, and for this coil we can say number of turns is N2. So this number of turns N1 and N2. So from here we can write mutual inductance is proportional to R2 divided by R. Okay, R2 divided by R. R2 square, sorry, this will be R2 square, this will be R1. So this particular formula, mu naught N1 N2 divided by pi R2 square divided by twice of R1. Okay, so R2 square divided by R1. We are getting this particular value for the mutual inductance between two concentric coils. Let us consider two solenoids A and B made from the same magnetic material of the relative permeability mu r and equal area of the cross section. Length of the A is twice that of B, and number of turns per unit length in A is half that of B. The ratio of the self-inductance of the two solenoid. What is solenoid depends on L equals to mu r into mu naught into N square pi r square small l. Right. So here were two solenoids. We can check it. They are having relative permeability, two solenoids made from the same magnetic material of relative permeability mu r and equal cross section area. So area is same. How they are differing? Length of the A is twice. Length of LA is twice of LB. So in the given question, what they mentioned is LA is twice of LB, and number of turns per unit length in A is half that of B. That is NA is NB by 2. So here we have N square factor is there and this L factor is there. So because of this, the ratio they are asking, so LA by LB is equals to NA by NB whole square into LB by L. Sorry, both are directly proportional. So this is LA by LB. So because of this factor NA by NB, how much we are getting? NA by NB, this is 1 by 2. So because of this 1 by 4, but because of this LA by LB, this is 2 times. So answer is 1 by 2. Okay, answer will be 1:2. This is LA by L, right? Because they are having same material, so mu r will be same, mu naught is same. This pi r square, that is area of the cross section, will be same. Two coils of self-inductance 2 millihenry and 8 millihenry are placed so close together that effective flux in one coil is completely linked with the other. So effective flux in one coil is completely linked with the other. So here we define one particular term, that is coefficient of coupling. What is coefficient of coupling? The coefficient of coupling is defined as K divided by K is given by M under root L1 into L2. What is L1 and 2? So if you have two coils, the first coil is having self-inductance L1, second coil is having self-inductance L2. Then the co-center coupling is defined as K is equals to M divided by under root L1 into L2. How they are coupled each other. This gives the idea about up to which extent they are coupled to each other. So in that case, we will be writing this K is equals to 1. Suppose if I K is equals to 1, this will give maximum flux linkage through each other. That is, so K is equals to 1. So M should be equals to under root L1 into L2, and this gives the maximum value of the mutual inductance between L1 and L2. So this M we can write here root of this L1 into L2. So what is L1? What is L1? What is L1? 2 millihenry multiplied by this 8 millihenry. We are getting how much? M is 16 millihenry. So this one is, answer is 4. Option is option D. So next we have alternating current. What is alternating current? The current which changes its direction with time. The current which changes direction with time. So this one is positive, negative, positive, negative, positive, negative. So the current changes direction with time. It has to change the reverse direction. Polarity should change. If you talk about this I versus T, and if you talk about this EMF, the EMF also changes its polarity. Again, this one is E versus T. And we can check again this side positive, negative, positive, negative, positive, negative. No matter what is the magnitude they are having, they should change the direction with respect to time. So in this case, we'll be writing that. So this is alternating current. We are having different circuits over here. First one is only resistance is there. Second is capacitance is only there, or inductance is only there. Third case, only capacitance is only there. Then fourth case, LR circuit will be there. Fifth one will be having RC circuit. Sixth one, that will be having LCR. So these are the circuits we'll be having. One thing that is common is that we define here impedance. What is impedance? Impedance triangle that we could focus in these cases. So we'll be making this side one resistance. This angle is phi, and this will be, if we have this side, will be having XL or XC. We'll be defining what is XL or XC, and this side we have R, and this will be Z. So this particular term is what we define impedance. And what is impedance? Z is given by under root R square plus XL square, or Z is, we can write here under root R square plus X square, or Z is what we define under root R square plus XL minus XC whole square, depending on the what type of element we have in the given circuit. If we have only L and R, we'll be using this particular formula. If we have only R and C, we'll be using this formula. If we have all LCR, we'll be using this only. In other case, if only inductor is there, resistance value will be 0. If only capacitor is there, again resistance value will be 0. If only resistance is there, then impedance value will be equal to resistance. So this is what different type of circuits will be having. Here we define some more terms, that is the phase difference and part difference. Phase difference and part difference. For example, L is only there in the inductor only. If we talk about, if there is only inductor in the given circuit, voltage is given as V0 sin omega t. Then current will be given by I0 sin omega t minus pi by 2 if there is only inductor in the circuit. And if there is only capacitor in the circuit, it will be reverse of the scenario. What we have, if the voltage is given as V0 sin omega t, then the current will be given by I0 sin omega t plus pi by 2. If we have resistor in the given circuit like this, so resistor in the given circuit will be like this. If we have this AC circuit, so in that case, the voltage is given as V0 sin omega t, and this will be resistance R. So current will be given by I0 sin omega t. So here sin omega t minus pi by 2 means current is lagging the voltage by pi by 2, and here the current is leading the voltage by pi by 2. In case of the capacitor, in case of the inductor, current is lagging it, and in case of the resistance, both are in the same phase, that is current as well as voltage will be in same phase. In other cases, if we have both the circuits or all three elements is there, that is L is there, C is also there, and resistance is also there, and it is connected like this, and voltage is given by V0 sin omega t. So in that case, we'll be writing what is V0 sin omega t. So this one is L, and this one is C, and this one is R. It depends on the value of the XL and XC. What is XL? The XL is given as omega multiplied by L. Omega multiplied by L. What is omega? 2 pi f into L. So XL is proportional to frequency. XL is proportional to inductance. Second, XC value. What is XC? 1 by omega C. This is the inductive reactance, capacitive reactance defined for the capacitor, and this is the inductive reactance defined for the inductor. we can say that this is the resistance of the inductor in AC and this is the resistance of the capacitor in DC, in AC only. So XC is equals to, what is that, 1 by 2 pi F into C. So here we can check it. Whenever we are getting whether the current is leading or lagging, that will depend on this case. If XC, if XL is greater than XC, so here inductive effect is more, current will be leading, current will be lagging here. In this case XL is greater than XC, and we have to make the impedance triangle. On this side we'll be making this side, what is that, XL minus XC, and this will be R and this will be phi. So here we will be adding this tan phi. What is tan phi? XL minus XC divided by R. And if we have second case, that if XC is greater than XL, so here I lags the voltage by how much angle? Phi angle. In the second case, if X is greater than XL, so this side, if X is greater than XL, means this will be again XC minus XL, and this will be R and this will be phi. So what is tan phi? The tan phi that will be writing here, XC minus XL divided by R. So here what happens? V leads I by how much angle? Phi. This second case. Now in the second, if we have third case, what is third case? If XL is equals to XC, so in that case this is VL is equals to VC. These two are we define as resonance condition. So in resonance condition, what are the things that will happen? So first point that we should write here, Z equals to R. Second point, resonance frequency we can calculate from here, that is omega is given by 1 by root of LC. So what is third point? That is omega. What is omega? 2 pi F is equals to 1 by root of LC. So from here resonance frequency is given by 1 by 2 pi under root L into C. The current will be maximum. The current will be maximum. I will be maximum. The current is maximum. Power also maximum. And what is power in AC circuit? The power in AC circuit is given by one formula, VRMS, maximum time useful, VRMS into IRMS into cos phi. What is cos phi? The cos phi is what we define R by Z, and this is what we define power factor of the AC circuit. We have power factor of the AC circuit. If there is only inductor in the circuit, only inductor is there, only inductor is there, the cos phi power factor value will be 0 because phi is pi by 2 in this case. The phi is the phase difference between current and voltage. Second, if only capacitor is also there, in that case also cos phi will be 0 because phi is again pi by 2. In this case capacitor is there, the current is leading the voltage by how much angle? Pi by 2. Third case, if we have only resistor is there, in this case cos phi value is 1, and 1 means R by Z is 1. So Z is equals to R. When the Z is equals to R, impedance is equals to resistance. Okay, impedance is equals to resistance. So this particular circuit, LCR resonance circuit, LCR resonance, XL is equals to XC. So that is also in this particular case, L is there, C is also there, and resistance is also there. And what happens actually in this particular case, this XL value and XC value are equal. So this circuit will behave as a resonance. In the resonance, maximum frequency will happen. So when XL is equals to XC, the circuit will become purely resistive and all the properties will be there. That is Z will be R, the cos phi value will be 1, the power factor value will be 1. So let's see some of the questions from this circuit. We have question from this. In the given figure below, the inductance L is connected to the AC source. The current flowing in the circuit is given by I equals sin naught sin omega t. The voltage drop across VL is given by, right? The voltage across VL is given by, what is VL? Voltage drop, maximum voltage we can write here, divided by XL is equals to I naught. Okay, so this I naught is the maximum value of the current we have. I naught is the maximum value of the current. So what is I naught? Voltage by resistance. So what is VL naught? That is I naught into XL. What is I naught? I naught only. What is XL? What is XL value? Omega multiplied by L. Right. Now here this is the maximum value, but we want in terms of the sine or cos. Now this is purely inductive circuit. As it is purely inductive circuit, current will be lagging or leading? Current will be lagging. I lags by voltage by how much angle? Pi by 2. So suppose if expression for I is given by I naught sin omega t, what is voltage across this inductor will be given by VL equals to, I'll be writing this particular term, that is maximum value of the voltage I naught into omega L sine omega t plus pi by 2, because current is lagging, so voltage is leading by how much angle? Pi by 2. So this sine omega t plus pi by 2 I'll be writing. So this particular term VL equals to sine something plus pi by 2 is cos something. So this will be I naught omega L cos omega t. Clear? So this particular term, the answer will be I naught omega L cos omega t. Answer will be option D. So moving to next question, where only capacitor is only there. A 10 microfarad capacitor is connected to 210 and 50 hertz source as shown in the figure. The peak current in the circuit, peak current means I naught. And what is I naught? V naught divided by Z. And what is Z here? Xc. Only capacitor is there. So we have to use Xc. So V naught divided by Xc. What is Xc? 1 by omega c. We have to calculate this. Okay. So let's calculate this. 1 by omega into c. So 1 by omega, what is omega? 2 pi f. 2 into pi into f. What is f? 50 into what is c? 10 microfarad. So 10 into 10 ki power minus 6. So this particular term we are getting 1 by omega c value. So that's it. Remaining part. So this is 15 to 200. This is 15 to 200. 1000. 10 ki power minus 6. This will go up. So this what we are getting here 1000 by pi is Xc value. Okay, 1000 by pi is Xc value. So this particular term, that is P naught by Xc. Xc is 1000 by pi we are getting. So 1000 by pi, what is P naught value? 210. This is RMS. If nothing is given in the question, remember this, this will be RMS. Nothing is given, we have to take this RMS. How can we convert into RMS to this? 212, 210 into root 2 divided by Xc. That is 1000 by pi. So this product term will go upside. So this will be 210 root 2 divided by 1000 into root 2 pi. So this will be the, and further calculation we have to do. So this 21 by 100, 21 into root 2, whatever the value will be getting, 21 into root 2, that is 1.4 into 21, and this is 3.14. So approximately that will be getting, it is more than, so if I solve this, this is 21 root 2 pi, 21 pi root 2 divided by 100. Okay. If I take the order of this, so 21 into pi, 21 into 3.14, 63 into root 2, 1.4. So this is approximately less than 1. 3 options are there. So this 21 into 3.14 into 1.4 divided by 100. So this side, so this we are getting approximately, this is 220 answer, we are getting approximately 0.93. Okay, 0.93 ampere. Right. So let's solve some more question from here. Now the circuit is LR. So we discuss L, we discuss the C. Now here will be LR, so means inductance is also there, resistance also there. So what they're asking, the value of the phi will be given by, what is value of the phi? Whenever they're asking value of the phi, draw impedance triangle. Impedance triangle you draw in a such a way that this angle is phi, that is the phase angle. So this angle is phi. The voltage is given at 200 sine 100 pi t plus phi. So in this case, this will be phi, and let's check this one. So this angle is phi, and this side we have XL, and this side we have R. This we have R. What is XL? The XL is omega times of L. And what is omega? So if we compare this, V is equals to V naught sine of omega t plus phi. So V is equals to V naught sine omega t plus phi. So what is omega value? Omega value from here is 100 pi. Okay. Omega t, that is comparing this with omega is equals to 100 pi multiplied by inductance. What is inductance value? 1 by pi. Pi or pi cancel. What is resistance value? Resistance is 100. Okay. So resistance value is 100. So this side, this particular value is 100, and this value is also 100. So this tan phi, what is tan phi? 100 divided by 100, we have 1. So phi is equals to 45. Clear? Phi is equals to 45. So this is use of the impedance triangle to calculate the to solve this type of questions we have. The net impedance of the circuit as shown in the figure will be given by, what is net impedance of the circuit in the figure? So here we have, in the given figure, we have the inductance, we have the capacitance, we have the resistance as well, and they're asking what is net impedance of the circuit. So what is impedance? Inductance is also there, capacitance also there, and resistance also there. So how can we solve this? I told you, make one impedance triangle. So first let's calculate what is the capacitive reactance, what is inductive reactance. So what is inductive reactance? Omega multiplied by L. What is omega? Omega we have, they're not mentioned. So omega is 50 hertz, they have mentioned, right? So this one is omega is 2 pi f into L. This is the value of the inductance, this is the value of the capacitance, and this is the value of the resistance we have. So this will be getting 2 pi into frequency. What is frequency? 50 into inductance is L. What is L? 50 by pi. Millihenry is there, multiplied by 10 to the power minus 3. Pi or pi cancel, 15 to 2, 100, 100 into 50. So this we are getting here 5000 into 10 to the power minus 3. This zeros cancel, we got here 5 ohm, that is the inductive reactance. Okay, that is inductive reactance. Let's talk about the capacitive reactance. So capacitive reactance is 1 by omega into C. So 1 by omega, what is omega? Again 2 pi into 50 into C. What is C? 10 to the power 3 divided by pi into 10 to the power minus 6. This pi and this pi getting answer 15 to 2. 15 to 2, we are getting 100, 10 to the power 3, and this is 10 to the power minus 6. This will go up. What is XC value? XC value we are getting here 10 ohm. Okay, XC value we are getting here 10 ohm. So if you make the impedance triangle, so this side, if you make the impedance triangle, simple triangle I am making. So this, as this is LCR circuit, we have to write this XC minus XL, and this one is R, and this will be Z. So what is Z value? Root of XC minus XL whole square plus R square. So Z value, putting this value, what is this? XC square. So this one is 10 minus pi ka whole square plus XC is 10, and what is XL? Pi. So 10 minus pi ka whole square plus R square. What is R value? R is again 10 square. So Z is given by root of this 5 square plus 100 square. So we are getting this 5 square plus 100, 125. 125 impedance, root of 125 is pi root 5. So this is the value of impedance we have, pi root 5. Clear? And if they're asking this particular angle over here, so tan phi. So what is tan phi? XC minus XL by R. What is XC minus XL? 10 minus pi divided by R, that is 10. So tan phi is equal to 1 by 2. So next question again from this LCR series circuit, we have inductance, we have the capacitance, we have the resistance value, and they're asking what across these they have given the voltage. Now in this case they have given the voltage, that is 40 volt, second is 10 volt, and third is 40 volt, and this is the source voltage we have. What they're asking, let's discuss this. Inductor of inductance L, capacitor C, and resistance R are connected in series to an AC source of potential difference V volt as shown in the figure. The potential difference across L, C, and R is 40 volt, 10 volt, and 40 volt respectively. 40, 10, and 40 volt respectively. The amplitude of the current flowing through LCR series circuit is 10 root 2 ampere. The impedance of the circuit should be given by, okay, right now. So whatever this value they have given, this one is RMS, this also RMS, and this also RMS. We have to calculate what is the current through it. So let's calculate what is the current also they have mentioned, that is 10 root 2. So what I can do, so this IRMS, what is IRMS? Is I naught by root 2. So what is I naught? Root 2 times of IRMS. So okay, the amplitude of the current means what they mention. The amplitude of the current flowing through it, LCR circuit, is 10 root 2. So this, so what is IRMS? We have the IRMS 10 root 2 divided by root 2 cancel. How much we got? 10 ampere. So that is IRMS. So this one is 10 ampere. And how can we get this net voltage? The net voltages will be writing this across. This one is VL, this one is VC, and this one is VR. Whenever this kind of question, again you make impedance triangle. You check between L and C, which one is having higher potential. Which one is having higher potential? 40, and this one having lower potential? 10. So this side will have VL minus VC, and this side will be having VR, and this will be V. That is the source voltage we have, right? So let's solve this particular question we have. So this will be writing this VL minus VC. What is VL minus VC? This side we have 40 minus 10, 40 minus 10, and what is VR we have? Across the voltage VR register, this is 40, this one is 30, and this is 40, so this will be 50 using Pythagorean triplets, 30, 40, 50. So source voltage that we are getting, VRMS is 50, VRMS is 50, VRMS value is 50. Okay, and we know IRMS. What is IRMS? Just now we calculate IRMS is 10 ampere. If we divide, what we're getting? VRMS by IRMS is what we got, impedance. So Z equals to VRMS divided by IRMS is equals to 50 by 10. Answer is 5 ohm. That is, impedance will be 5 ohm. Answer is option A. A series LCR circuit connected to an AC voltage source. When L is removed from the circuit, the phase difference between the current and voltage is pi by 3. If C is removed from the circuit, so here we have LCR circuit, right? This one is LCR circuit. What we are doing, first case, what we are doing, if L is removed, when L is removed from the circuit, there will be only capacitance and resistance is there. So in that case, what we will be writing, only capacitance is there and resistance is there. In that case, we'll be writing, what is the phase difference between the current and voltage is pi by 3. If instead C is removed, so here the phase difference between current and voltage is pi by 3. So here I'll be writing 10 phi is equals to 10 pi by 3, and in pi by 3 only capacitor is there, so this will be XC divided by R. Next, second case, what is happening? If instead C is removed, if we are removing this C, when the C is removed from the circuit, the phase difference is again pi by 3. So in this case, we have the inductor and we have this resistance over here. Now the phase difference is again pi by 3. So 10 pi is 10 pi by 3 is equals to XL divided by R. Now this one and this one are equal because both are having pi by 3 phase difference. So I can write here XC by R will be equals to XL by R. And from here we are getting what? XC should be equals to XL. So when this condition is satisfied, what is the power factor? Power factor is nothing but unity, because cos pi by Z, cos pi, and what is the cos pi? R by Z, and this is resonance. In resonance we have Z equals to R. So power factor is unity, that is 1. Okay. So again, the potential difference across the resistance, capacitance and inductance are 80 volt, 40 volt and 100 volt respectively. The power factor of this circuit will be given by across the resistance, we draw the resistance, across the capacitance, draw the capacitance, and across the inductance. So this will be, and let's talk about this one. So across this potential difference is how much? This one is 80 volt and this capacitance value is 40 volt, and across this inductance, what is this? 100 volt. The power factor of the circuit will be given by, what is power factor? The power factor is given by, again, from the, we have to make the impedance triangle. Now they make the impedance triangle in a such way that this particular angle should be phi, and this side, this perpendicular will be given by this VL minus VC. So we are getting how much? This 100 minus 40, 100 minus 40, this one, and this side we have resistance, that one is 80. So this cos phi, what is cos phi? R by Z, and that is not required. At this point we can directly say this one is 100 minus 40 means this one is 40. Okay, so this is 100 volt and this one is 40. So this one is 100 minus 40. So this one is how much? 60. Okay, this will be 60 because this is 100 minus, we are having 100 minus 40, that is VL minus VC. This is cos phi, and what is cos phi value? The cos phi value is given by 80 by 100. So this we are getting here 80 by 100, that is 0.8. Cos pi is 80 by 100, 0.8. So what is pi value from here? This cos pi is 0.8. This is what power factor we have. That is answer is 0.8. The instantaneous values of the alternating current and voltage in the circuit is given by, so I is equals to 1 by root 2 sine of 100 pi t, and this E is equals to, they have mentioned, that is E is equals to 1 by root 2 sine of 100 pi t plus pi by 3. If we see the phase difference between these two, pi, what is pi here? Pi is pi by 3. If you see the phase difference between these two, what they're asking, average power. What is average power? The average power is given by Vrms into Irms into cos pi. And what is cos pi? Pi by 2. What is Vrms? What is Vrms? So here Irms, what is Irms? 1 by root 2 times of root 2, we are getting this 1 by 2. And what is ERMS? ERMS will be having again 1 by root 2 times of this root 2 is 1 by 2. Okay, so this we are getting, so average power that we are getting Vrms, what is Vrms? 1 by 2 into Irms, again 1 by 2 into cos, what is pi? This will be cos pi by 3. So we are getting 1 by 2 into 1 by 2 into this cos pi by 3, that is 1 by 8 that we have. So this answer is option D over here. Anyway, it's not here, this answer option D, 1 by 8. Okay, so this we are using the simple formula. What is that? Vrms Irms into cos pi. Vrms is I naught by root 2 and IR is also I naught by root 2. Okay, so last topic is that what is transformer that we have. Transformer will be having two coils. One coil this way, that is we call it as primary coil, and second coil this way, that is we call it as secondary coil. This is where the AC is input fed into this transformer, and this is where the load is connected on the other side. This is also we call it as, this one is primary circuit, this one is primary circuit, and this will be secondary circuit. Okay, this will be secondary circuit. This one is primary windings, primary, and this will be secondary. This particular voltage we have, we call it as Vp, that is primary voltage, and whatever current that is flowing here, primary current. Number of turns here will be primary, number of turns in primary. This is number of turns in secondary is Ns. So here this will be Ns. And this particular voltage, what we got, that will be secondary voltage will be having. Current will also be secondary. So for ideal transformer, for the transformer we have Vp by Vs. Vp by Vs is equals to Ip is equals to Np by Ns. Number of turns in, so voltage across the primary divided by voltage across the secondary is equal to number of turns in primary divided by number of turns in secondary is equals to Is by Ip. So this result that we have to remember this for transformer case. If the transformer is ideal, we define one more term, eta. What is eta? Output power divided by input power. Now two cases will be there in which transformer will be ideal. Ideal transformer means there is no energy loss. Whatever the energy we are feeding on this primary side, the same energy will be going on the secondary side also. No energy loss. If it is ideal, eta value is 1. So output power will be is equals to input power. In that case, eta value is 1. So Vs into Is equals to Vp into Ip. That is this output power and this one is input power. If the transformer is not, eta value is given by output by input, and if they are asking in terms of the percentage, this will be 100%. So this eta is given by output power Vs into Is divided by Vp into Ip multiplied by 100%. This is efficiency of transformer. So there are some more points in the transformer, like how the what are the different losses. We have hysteresis loss, we have the eddy current losses over here, we have the flux losses. So go and read the NCERT for those things. So let's solve this particular question. Step up transformer. Step transformer means step up. It will step up the voltage. Initial voltage of the final voltage will be higher than initial voltage. That is step up transformer. Step down transformer, the final voltage will be less than the initial voltage. So the voltage in primary, it is stepping up. So voltage in secondary will be more than voltage in primary. Step up transformer is connected to an AC main supply of 220 volt. So this VP value is 220 volt. Operate at how much? This one. To operate at 11,088 watt. The current in the secondary circuit ignoring the power loss. So here we can write VP is this much. And what is output? The output voltage has to be, in this case, 11,000. Okay. And what is output power? The output power is also 88 watt. The current in the secondary coil ignoring the power losses, the transformer will be given by. So how we can solve this? Step transformer is connected to an AC main supply of 220 volt to operate at 11,088 watt. 11,088 watt. The current in the secondary circuit should be given by. So here we can write VP into IP is equals to VS into IS is equals to how much? What is power output? 88 watt. So from here we can calculate this. So what is VS? 11,000 multiplied with what is IS? That is what we have to calculate, equals to 88. So what is IS value? So this 88 divided by 11,000. We are getting this how much? 8 milliwatt. Answer is option. So these are the topics we have for these two chapters. Again, the chapter is having 1 or 2 questions expected. Definitely one question we can expect from this topic. And this is simple formula based question. Little bit theory is involved where we are finding the direction of the Lenz law, and most of the questions we can solve it from the formula from both the chapters, alternating current and EMI. Tomorrow we'll be discussing the optics. Yes, the highest weighted chapter we can say, the more weighted chapter. Reflection is there, refraction is also there. Reflection is for the mirror. We'll be discussing different types of mirror. Spherical mirror will be there, spherical mirror, concave mirror, convex mirror, and their image formation. Next we have refraction. In the refraction we'll be having lenses, we have the prism as well, and we have the glass slab as well. And last part that we'll be having, that is optical instruments. So these are the topics that we will try to cover tomorrow. So till now, prepare well, all the very best, and in your preparation. So keep practicing, and see you tomorrow.